Okay. All right, let's get started. Yeah, we're 2 minutes early. That's fine. Okay, I'm Kilpatrick. I work on layout team. I'm here to convince you that no one knows anything about block layout or how mountain collapsing loves floats. Quickly, a few bits of terminology. Oh God, what's this microphone is all Stay up. Let's have the computer to stay up. Okay. A formatting context is basically a completely new layout mode. This is something like, Flexbox or Grid, or what's known as new block formatting contexts. New block formatting contexts are a bit confusing because something that has display block is not necessarily a new block formatting context. You're in the right place. Things like floats, things that have overflow hidden, but a regular display block is not a new block formatting context. It participates in its parent or an arbitrary parent's block formatting context. The reason for this is that things like floats and things like margin collapsing can intrude through these things. We'll get to why this is important in a second. Layout NG terminology. Layout NG is sort of built around the fact that we have immutable inputs and outputs. The outputs of a layout, laying out a node in layout NG is two things: a physical fragment. This could be, if you saw a Mills talk, a text fragment, a line box fragment, a box fragment. For almost all block layout, these are just box fragments. The information that these have on them are very, very simple. It's just the width and height of that fragment, and eventually where the parent will position it. Most of these things will contain children, so they also have a vector of children as well. Any questions so far? No, great. A layout result holds onto a physical fragment, but it contains a whole bunch of other stuff that painting doesn't need. So this is things like margin struts, VFC offsets, which we'll get to a second. There's a lot of extra information that needs to be communicated between parent and child in layout that isn't just the raw geometry of a box. The inputs. Firstly, the constraint space is the major input. This has all the information that a parent wants to give to a child layout. So this includes the available space, percentage, what size to resolve your percentages against, which is different to the available space often, where that child should try and fragment. We may rename this because it's kind of an overloaded term now. A constraint space also has an exclusion space. Floats are very, very special, so they get their own object to pass between child and parent. You also have the NG node. We have two types at the moment, blocks and inlines. And we also have a break token. We won't get into how fragmentation works in layout NG today, but basically a break token is an extra bit of information that we tack on and pass from parent to child, which basically says, you already gave me like 2 fragments, I want you to start producing the 3rd fragment. And so I'll tell the child, you've already consumed 200 pixels of space and a bunch of other information. The break tokens sort of form a tree down, so a break token might hold on to other break tokens for its children. This is if you take one thing away from this talk, this is the most important slide. Inputs and outputs of layout NG are immutable. We do not do things like we do in the current layout code base by like walk up to the containing block and then modify something and then walk all the way back down. If you break this, I will come and hunt you down. We currently enforce this by const correctness. Please don't break it. It's the most important flag because I also use hopping, which is my favorite CSS. Questions so far? Okay. Inputs, outputs, what are they? Immutable. Hey! All right, good. Margin collapsing.
Can you say again how you enforce this?
Const correctness.
Const correctness.
Yeah, we just basically label the inputs and outputs as const and make sure that no one,
throws it that way.
Yeah, exactly. Margin collapsing. So the problem with block layout is that you first need to understand all of the really, really ugly bits of CSS to properly implement it. I've come to learn that there's probably about 4 people in the world that actually understand all of this. I'm hoping to grow this number slightly enough, so let's get into it. Does anyone know what margin collapsing does? Yes, Alex.
Well, it collapses, you get like one margin, another margin, and there are rules for how they combine and collapse together.
Yes, exactly. So basically, you can see this happening here, is that A has a bottom margin of 20 pixels. I've sort of drawn little boxes there that are 10 pixels in size. B has a margin top of 10 pixels. Other layout engines will space these things 30 pixels apart, 20 plus 10. But in CSS, due to margin collapsing, it basically takes the largest of the positives. So you can see this here. If I bump this up to, as soon as I go over 20, it picks B's margin top as a thing to space them. Pretty straightforward. Does anyone want to guess what happens when I go negative? What CSS does, in all of its wisdom, is it takes a look at the maximum of the positive margins. It also takes the minimum of the negative margins and sums them together. So in this case, you see 20 minus, plus negative 10. If I bring this down to negative 10, nothing happens. But if I bring it down further, then that negative will start to impact where it is. So, what are the rules? Margin collapsing. It's the sum of the maximum positive margin that we've seen and the minimum of the negative margin that we've seen. This is all that you, with these two, like one rule plus 2 sub-rules. This is all that you need to know for how margin collapsing works. So, where this gets complicated is that they are shared, one margin is shared between possibly multiple boxes. So here we've got 2 divs. B is nested inside of A, and they both share a margin top. Because there is nothing separating these boxes, so something like a border or some text or something like that, they share the same margin. So here's A's margin top, basically quote unquote wins because it's larger than B's. I can increase this one, and the same rules apply. Oops. So nothing happens when I'm modifying B, but as soon as B is larger, it kicks in and starts moving it up and down. As soon as this goes negative, what's going to happen?
It'll start subtracting.
It will start subtracting.
Including moving A up.
Yeah, including moving A up. So basically, their position is dependent on one another. So, we can get more crazy. Same rules apply. The largest one wins.
Can you describe out loud what you have on the slide there?
Yes, I can try. So I've got now 3 divs nested inside of each other. All of those divs have a margin top with nothing separating them. And one of them has text inside of them. And so margin top of A, margin top of B, margin top of C, I'm basically just fiddling with them. But basically, the largest one wins. As soon as one goes negative, that also contributes to the sum. So here we've got 60 is the biggest, negative 20 is the smallest, and so now they position 40 pixels down. If I create one that's got a larger negative, that starts to impact.
So,
Yes.
fundamental question.
Yes.
What CSS spec guys? What is the real world usage?
That's a good question. So the first one that I showed makes sense, where you're actually trying to separate 2 boxes. This sort of makes sense. You actually you want the margin bottom and the margin top of 2 adjacent elements to be shared and to take the maximum. The fact that this happens here, I don't know.
I think it goes all the way back to CSS1.
Yeah.
So
Yeah.
probably hopeful of that.
Yes.
Does this still apply if you have elements that define just a margin as opposed to a margin top / margin
Yes.
bottom,
Yeah.
and then they get like automatically wrapped? So they used to be next to each other and now they're above and below each other.
So this only happens for block flow layout. The other margin, like the other modes, so flex grid, they don't collapse margins,
Okay.
which is a good thing. This only happens for block layout, basically.
Right.
Okay. Now, here I have got 3 divs. One suspiciously is empty, and it's got a margin bottom. What's going to happen when I increase the margin bottom here to 30? Oh my God! What just happened? Empty divs, so empty blocks, are special. Basically what happens is that margins collapse, quote unquote, through them. This is an awful idea. I think this was added to CSS. Someone told me something about discouraging people from using paragraphs to do something about anchoring. I don't know. It is the worst idea. But basically, if you have an empty div like this, the same rules apply. But now you need to incorporate the bottom margins as well in the calculation. So here now, the largest positive is 30, which is B's margin bottom. The smallest negative, -10, and so all of that group of elements are all positioned at 20 pixels down. Okay, how are we going? Oh yeah, here we go. Margin collapsing, empty box, those collapsing through. Terrible idea. This can get arbitrarily complex. So you can actually nest empty divs inside of one another arbitrarily. And so the same things apply. So if I twiddle C's margin bottom now, that will have an effect of that whole group. Okay, are people getting this? Yes.
Does C's margin top collapse with its margin bottom?
Yes.
Yeah.
Yes. See, completely, as soon as we go over, and then as soon as it goes negative. So basically what happens is the sort of quote unquote top margin for this whole group is the largest of the positives that you see plus the smallest of the negatives summed, and this includes the special empty blocks which sort of they collapse through. So you just consider them like a margin top. This sort of gets into the problem with this because you have no idea where to position B and C until you've seen D's margin. Because D could be, negative, for example. So you have no idea where A, B, and C are going to be within inside of this formatting context until you've seen D. Okay. This also works, I've been only showing things that look at top margins. This also works for bottom margins as well. I've just added this here, but you can convince yourself that, so I've got A, which has a nested B, and then a series of empty divs inside of A, and then finally something next in flow, which is called E. Basically the same rules apply on the bottom as well. So you can construct arbitrarily complex margins at the top, arbitrarily complex margins at the bottom of the box, and you have to get this all to work.
Left, right? What about left, right?
Left, right is okay. We only need to, margin collapsing only happens in the block direction. So we only need to consider the block start and the block end. So concretely this means in horizontal top bottom writing mode, you only need to consider the margin top and margin bottom. If you're working in a vertical writing mode, you need to use the margin left and margin right. Layout in G has much better support for writing modes than the current layout system, simply because we only operate in the logical writing mode of block start, block end, inline start, inline end. And this makes, we've wiped away a whole class of bugs that are filed against us for this. So whenever I say like margin top here, think margin block start. But that's sort of foreign to most people, so I don't use that. So how do we do this? Margin collapsing. We have a tuple, which is the largest positive that we've seen and the smallest negative that we've seen. It is both an input and output to layout. So a parent will give a margin to its child, and then the child may do something with that margin struct, and it may pass it directly back out if it's an empty block as a result. So concretely, what does this mean? Now let's go to pen mode. Thanks, Windows. Screens, okay. So in this example here, hey, what's, okay. All right, also works, all right. So basically, there's a div surrounding all of this. We have a tuple that starts out as 0, 0. The parent will look at A and go, aha, you have a margin top of 20. Great. It will pass this div into A. A will look at its next child B and go, aha, you have a margin top of 10 pixels. 10 is not smaller than, this is a bad example. I need something more interesting here. Here, let's change this to 30. It will pass it into B, and it will look at B and go, oh, you've got a margin top of 10 pixels. That doesn't win yet, so I'm just going to pass the margin struct straight through. I'm not going to modify it at all. B will now have it, and I'll look at C, and it'll go, oh, you've got a margin top of 30. That wins. I'll change my margin struct to 30. And now we will start passing it back out. So C's result will be a margin of 30, 0, and we'll do the same for the bottoms on the way out. So you can sort of see that the margin struct sort of threads through all of your divs as an input and output until we hit something that what's called something resolves the margin struct. Question? No, just go. Oh, it's been exciting for a second there. But the key thing to realize here is that it's basically just sort of threads through the whole layout tree until something can resolve it. So the way that we solve how we do positioning in layout in G for blocks is that we have a special offset type called a BFC offset. Basically what happens is, basically the whole problem with block layout is you can't really do anything correctly unless you know where you are relative to your parent, relative to the arbitrary parent, which is the new layout mode, the block formatting context. Again, it is a tuple. It contains effectively an inline offset and a block offset. It's lined to deal with LTR crazy. And the child basically may choose to, quote unquote, resolve its BFC offset. This is done when, in the previous examples, we come across something like text, for example. As soon as we see some text, we look at our current margin struct. So in this case, I might make it a little bit more interesting. Bump this up to 30 and make D negative. So in this case, our margin struct, right before this text here, is going to be 30 and negative 10. We just go, oh, we've got some text. I now need to position myself within the block formatting context. I'll sum these two numbers together, and that results in the 20 offset in the block direction. A child will position itself within the block formatting context under the following set of circumstances. If there's any border or padding block start or block end, if it's non-zero height, so it's actually got height 20 pixels on that div, If it's a non-empty inline, so you can just have you can have empty inlines, like just a span that has no text in it. So you actually need something that has text, or if a child has clearance. And this is where anything that's not one of those things is effectively an empty block where it cannot position itself within the block form lane context yet. So a good example here is that B and C don't know where they'll end up yet. It needs to rely on an arbitrary sibling somewhere in the tree to actually position them.
And if you get through this whole tree and nothing is empty and resolves it, do these just not get laid out at all?
So they do get positioned. What happens is at that stage, we know that you're an empty block, and we've reached the root of the layout, which is the block form main context. We take your end margin struct and we position you that way.
Okay.
It's basically it's what all the engines do, but it's very hard to reason it out, why something will get positioned that way. There's sort of one example here. You can see like this purple thing is weirdly like not on E or not on A or E. This is that case basically. It's actually not, it doesn't like bubble up to the block forming context. It may get positioned by just a parent that knows where it is within the block forming context. It's very subtle. So as a consequence, we have two classes of objects. Basically something that knows where it is within the block forming context and something that doesn't. And this is what we call BFC offset propagation. And basically what happens is the position of the child sort of bubbles its way up to the tree. And we basically solve this resolution with this table here. So if a child is empty, it doesn't know its BFC offset yet, and a parent also doesn't know its BFC offset yet, the parent will position its child basically at 0. And this is sort of what you see with all of these examples here, is that B positions C relative to itself at 0. They're on the same line. They have to be. The next example is, this is an example which you just asked about, in that if we've got an empty block and the parent knows where it is, the parent will just use this end margin struct. If sorry, that was the case. If both of them are known, where's none? Yeah. So if both of them are known, we can just do one offset minus the other to work out the relative difference between the two. This can happen. This is sort of somewhat the usual case. And there's one that I got messed up. Okay. Stretch. You now know more about margin collapsing than most, yeah. Congratulations. Floats. Does anyone have any questions about margin collapsing now? Does everyone sort of roughly work out the mental model? All right. Yes. Question.
What's the case where they trigger relayout?
Yeah. So this actually gets into floats.
Okay.
Yeah, I'll show you this. It's fun. Floats. Okay. Floats, two types. Float left, float right. Floats are positioned in what we call the first layout opportunity. And the other final rule that you need to know about is that they always align their top edge. So it's impossible to position a float and then have another float positioned above it. This happens if this thing might have clearance on it, for example. This basically can't happen. This edge will get shifted down to align with this line here. That's what that rule is. So here I've just got a bunch of floats of differing heights. And I'm going to change the final float's size. And so what happens is it's going to walk through a bunch of layout opportunities. So what we consider a layout opportunity is that it's just areas that a float can fit inside. So here's the first layout opportunity. The next one is the next widest area in the block direction. The next widest one is this one, and so on and so forth. And then finally, arguably there's one down here. This is used all throughout a lot of different things in block layout. This wasn't a first-class citizen in our current layout engine. We've got a few bugs because of this, but it's basically how floats position themselves. So as I slowly increase ease width, where's it going to go next?
Below R.
Which R?
Left myself.
Pink one.
The pink one. I heard the pink one. Well, hey! Okay, if I keep increasing it, where's it going to end up next?
Below L.
Below L. Hooray! Where's it going to end up next? Hooray! And where's it going? Oh, where's it going to end up next? And so this sort of shows you what layout opportunities do. Is we have them as a first-class citizen. We can sort of quickly determine the space that a float will fit in via some interesting algorithms. Yeah. Any questions on this so far? No. Great. This sort of shows you layout opportunities with inlines. So you can sort of see here that bunch of floats again, a bunch of X's using the ahem font, which just render as squares so you can see them easily. A line will always lay out inside of an layout opportunity and try and fit there. If it doesn't fit within a layout opportunity, it will get pushed down until it finds a layout opportunity that it does fit inside of. So here's sort of the first one. We start here looking for the next layout opportunity. We do here, and this lays out these two boxes, washer and swimming. So you can see sort of how inlines now flow around fonts. This sort of illustrates also why knowing your position relative to the block formatting context is so important, because you could have floats arbitrarily before you as siblings that may affect where you get laid out. So this is one of the problems with block layout, is that you always have spooky action at a distance. Okay, all of the float logic in block layout is encapsulated behind a class called ng-exclusions place. This is a glorified vector of floats, but this is the interface that we use to find these layout opportunities from a given point. So in this example here, you sort of need to start searching for layout opportunities, not at the top, but from where the next line needs to be laid out from. And basically querying a bunch of things about floats. So the top start edge to do the top alignment rule, and the block end to implement clearance. Okay, are we ready for margin collapsing and floats? I see.
I have a question about floats. If you have a float that's also positioned, does the position offset influence the layout opportunities? Or are they based on the static?
So the position of the float, we need to position it first because that will change the static position. But if it's then out of float positioned, then I think it doesn't get added as an exclusion.
What if it's relative?
If it's relative, it does. But the shifting it will not. The exclusion will stay the same.
Oh, I see. So you can't exclude arbitrary
options. So if I change R's, now we get to see if what I said is true. If I do relative, then top, it doesn't change the underlying line layout, which is a good thing. This gets into the relayout case that you're asking about before. So here we've got, inside of the new formatting context, firstly, one float left, which is this big blue L. we have then an empty div. Inside of this empty div is a float left, which is the purple float, and another empty div as a sibling to that float. So it's afterwards in the DOM tree. And then finally we have E. So what's going to happen if I change D's margin top here? So firstly, what's going to happen to the yellow line, which is all of the empties? It's going to move down. This is the same margin collapsing rule applying. So basically, to position effectively E, there's a little bit of weirdness going on here, but effectively E, you need to look at the largest positive margin that you've seen plus the smallest negative margin. And so this will shift everything down. The problem with this is that the position of L depends on something later in the tree. When we come across a float inside of an empty div or something that hasn't resolved its BFC offset yet, we have no way of determining where it's actually going to be laid out and consequently where everything else below it is going to be laid out. This is probably the most complex part of block layout to implement in layout.ng. We get, and also in our current engine, we get a bunch of cases wrong related to this stuff at the fringes. The common cases we get right, but you can expand the case to get more and more convoluted, and we start to drop off. And so just to reinforce that point, you sort of have no idea where to start searching for layout opportunities based on the width. There's just no way of positioning this flow. And yes, question.
Are there cases where the relay layout is not stable?
No, there are not.
Okay.
So basically what happens here is that E, which is the first thing that has text in it. Why can't I select? There we go. iframe's not focused. E is the first thing that resolves its BFC offset. As soon as we detect that, we actually abort layout. We just go, oh, hang on, I know a BFC offset. Position all, and if I've got unpositioned floats, so this float left here is an unpositioned float, meaning that we don't know where it's going to end up yet. Relay out that whole subtree, now assuming that this is going to be your position. And then we continue from there. So we now know where, the offset on which L should start looking, the purple float should start looking for layout opportunities. And we lay out exactly the same as we do before, but we've just got an extra if can actually position them. And then finally, we hit E again and it goes, oh great, I can't see any unpositioned floats. I'll continue with layout. And this basically summarizes that. So now as an output to layout, we also have a list of unpositioned floats. This should only be populated if it's an empty div. And this is basically what I just said. As soon as something resolves a BFC offset, we abort layout, relay out anything that had unpositioned floats. A constraint space also has an input with a list of unpositioned floats, and this sort of threads through like the margin strut. This is because positioning new formatting contexts is super fun. All right, how are we going?
2 minutes over.
2 minutes over. Sweet. Finally, margin close plus clearance. Basically, clearance isn't as simple as you think about, mainly because something arbitrarily further in the tree can affect if you should adhere to that clearance or not. So here, B has clear left on it. The margin of D will affect if you actually need to clear the element or not. It affects what the position is. And the TLDR is that we pass a clearance offset from parent to child. And as soon as something resolves its BFC offset, we adjust it to that clearance line. Hooray! You made it. I didn't cover a lot of things. These are a list of things I didn't cover. Any questions?
So this algorithm or latency can help to the hit testing on float.
So I don't know. Currently, we're copying back all the data structures into the old tree, but we're not copying back the floats that aren't painted.
Yeah, I'm not sure about detail about hit testing on
Yeah.
float, but it seems to be a current implementation of hit testing on float is broken.
Okay, this may help us. This may result in stabler positions of floats. And like eventually, we want to actually put floats into the fragment tree like properly, and like once we paint from directly from that, it might improve a bunch of things because we won't have the floating objects data structure anymore. But that's like a year away at least. At some stage, we will get rid of like the floating objects data structure, I hope. But I might be wrong there. Cool, that's it.